Okay, we'll move on. Is Nicolas Martin?
All right, so thank you very much. I apologize for not being in beautiful Quebec. I wish I could be there with you, but I had a commitment here today in Strasbourg. Today I'm going to talk about the Pristine survey, now the Pristine Large Program. It's a bit of an oddball because we actually started in 2015, but we were just awarded a large program for 2025B to 2026B. And so I'll explain why things evolved this way. I wanted to give a shout out to the whole collaboration. It's about 50, 60 people now. And in particular to my co-PI, Elsa Starkenberg at the University of Groningen. So the goal of the Pristine survey is to get the metallicity of stars in the Milky Way, and in particular to try to find the most metal-poor stars of the Milky Way. And the reason for this can be seen right away on this plot that you have on the right here, where in a set of simulations, you look here at stellar particles in the simulation, their age of formation. This is the Big Bang here on the left, and we're now at almost 14 billion years after the Big Bang. And on the y-axis, what you have here is the metallicity of a star. At 0, Fe over h of 0, it's solar metallicity, and Fe over h of, say, -3, you're at 1,000th of the solar metallicity, iron to hydrogen ratio. And you can see very easily that if you're able to find stars of such low metallicities, -3, -4, and below, you know that you're observing stars that were formed over the first 1 to 2 billion years after the Big Bang. So maybe the very first stars are unreachable because they're thought to be very massive and therefore to die in supernovae very quickly, supernovae, hypernovae, some weird objects very quickly. But they enrich the next generation of stars, and we have the hope of being able to tease out the properties of the first stars in the second, third generation stars. These stars have very, very low metallicities. And at the same time, if we can find stellar structures in the Milky Way environment that are made of those stars, then we can hope to understand how the first, for instance, clusters of stars would form 13.5 billion years ago. This is very complementary to what's being done at the very moment with JWST or HST in the case of this particular example. You may remember a couple of years ago, there was this idea that a star on a magnification arc through strong lensing might be, or an object might be a star observed from redshift 6.2. It's still very debated, but even if it's not a star, it's likely to be a star-forming region very early in the age of the universe, and we can locally find the counterparts to these objects. What we cannot do at high redshift, but we can do locally, is go and get elemental abundances for these stars that are second-generation stars. For instance, you have a work here from Vinny Placco where you have some chemical abundances measured for some particular elements, and the different zigzagging lines here are the elemental productions of different types of first stars, where you can vary the mass, you can vary the energy of the explosion as they die. And you can see in this particular case that this particular pattern of elemental abundances is well reproduced by a first star of about 10 to 12 solar masses. So if we're able to build a large sample of those stars, then we can hope to really understand better how the first stars formed, what elements they produce, and this is very much at the basis of everything that comes later. Now, the one drawback is that these stars are incredibly difficult to find. If you go for a random survey of the Milky Way stars, what you find in this plot showing different metallicity distribution functions is mainly thin disk stars in the solar neighborhood, bold stars if you go a bit further into the Milky Way. These are all very metal-rich objects with metallicities that are close to solar, going all the way down with the long tail to metallicities Fe over h of -1. You can go to the thick disk, it goes a bit further down, but it certainly doesn't reach these very, very low metallicity regimes. So you have to go to the halo of the Milky Way. There's already only 1% of the stars in the Milky Way, and then you have to look at the very low metallicity tail of this particular component of the Milky Way. At the moment, there's about 40 stars known with an iron abundance, Fe over h, below -4. And so this number needs to increase significantly if we want to have any hope of trying to piece together what the properties of the first stars are. So one obvious way to do such an exercise is to do a metallicity survey that is tailored to this low metallicity tail. And so that's what we started in 2015 with the Pristine survey, which is a single band survey of the Milky Way sky using the calcium H&K narrowband filter on CFHT that was built in 2014 or so. So we've really benefited from this new set of filters. It's also a bit of a unique, largish program because we're using bad weather conditions. We're probably the only ones who are happy when the weather is good enough to observe, but not good enough to do really superb quality science, because then we end up getting a lot of that time. Joke aside, what we end up doing is helping CFHT continue to run the telescope to do useful science even when the conditions are not optimal. And so we've been accumulating about 170 nights of telescope time since 2015, over the last decade. At the moment, we've accumulated about 14,000 images to tile as much of the sky as we can. So these images, because it's bad weather conditions, have to be repeated, but it's not a huge cost for time that otherwise would not be used by the telescope. And so far, we have about 47 papers that we've been writing since 2017, presenting various goals of the survey. This is a somewhat outdated image of the footprint of the survey. You can see that it's mainly covering the North Galactic Cap and the South Galactic Cap. By now, some of these holes here have been filled in over the last few months. But you can see that there's quite a few holes because of this bad weather strategy. And so at the moment, we're kind of working hard on trying to fill in the holes before extending the survey to other regions. We do have an extension to the Milky Way belt where it's expected a lot of these old stars are actually residing, even though it's quite difficult because of the amount of extinction and crowding that you have in the belt. At the moment, we have about 7,000 to 8,000 square degrees of coverage in the Milky Way sky, mainly regions away from the disk of the Milky Way. So how does it work? What can you do when you have a calcium HNK observation of stars? This is a model of the star solar metallicity. This is a low giant with a particular temperature, and this is the spectrum that you get if you look at spectral libraries, synthetic libraries. You see that you have these two very large lines, calcium H and calcium K, in this part of the plot. They're very large because there's a lot of calcium in that star because the star is solar metallicity. And this is in black, the filter curve of the calcium H and K filter. So if you change the temperature of the star, the spectrum changes its shape, but overall you still have these big fat lines that are present for a solar metallicity star. And so then what you can do is report the position of that star. If you integrate the spectrum under this calcium HNK filter and also nearby medium band, large bands like G and I from SDSS, for instance, you can report the position of that star in a combination of those filters. And that's what I'm showing here on the left. Where on the x-axis, you have G minus I. This is a proxy for the temperature because we saw that as the temperature changes, the depth of the lines change. And on the y-axis, what you're basically comparing here is calcium HNK with the G band as just redwords of it. So what G band tells you what's the flux of the star, what you expect for a black body of that color in the G band. You extrapolate that to the calcium HNK band. If you have way less absorption, that will be the case here. If you have a lot of absorption, the flux will be way lower, and you can report these three particular examples on the plot, and they lie down here. Now you can start tweaking the metallicity of the star. This is what happens with metallicity -1. It's not very impressive. It changes the position of the stars in this color-colored plot, changes a little bit, but not too much. But look at what happens when you go to metallicity -2, -3. You're talking about changes of about 0.2, 0.4 magnitudes to separate those stars from stars of solar metallicity or metallicity -1. So if this really works this way with real stars, then it should be fairly easy to isolate stars of very low metallicity, -2, -3 and below, from the bulk of the stars of the Milky Way that have solar metallicity to metallicity -1. So this is all theory. It's actually from the proposal that we put in 2014. This is what happens in real life. The lines I was showing you before, it's these dotted and dashed lines. This is for models for metallicity -3, -4. The only change here from the plot before is that we switched to the Gaia bands now. And what you see, all these dots are real observations of stars observed by SDSS and Segway, for which we have a spectroscopic metallicity. And you see that it works beautifully with the metal-rich stars being at the bottom of the plot and the metal-poor stars being at the top. So we have a very efficient way to isolate stars of low metallicity and go hunt for these fossils of the early ages of the universe. We've calibrated this whole relation. This is the results of our calibration compared to a validation sample coming from high-resolution observations of metal-poor stars. And you can see that we have a very good correspondence between our metallicity on the left here and the spectroscopic metallicities on the x-axis, down to metallicities about -3.5 or so. So soon after we started the project, 2015, 16, 17, we launched into a very large spectroscopic campaign using smallish telescopes, 2 to 4 meter telescopes, mainly the INT in the Canary Islands, but also Espadon a little bit, and Graces, to confirm, first of all, the success that we have in discovering very middle poor stars. We confirmed that about a quarter of the stars we think are below middle St -3 actually really are below middle St -3, which may seem like a small number, but the previous surveys were more like 3 to 5%. So this is significantly better. And the other real benefit of this technique is that 90% of the other stars, if not more, are actually below middle St -2. So they're still interesting halo stars and not contaminants from the Milky Way disk and Milky Way foreground. We've been following up also with spectroscopy at high resolution to get the chemistry of some of the most middle poor stars. I don't have time to get into the details. There's quite a few papers on that. But I wanted to show you the example of one particular star. This star, which is the lowest middle St star that we found so far with an FE over H of -4.4. What's quite striking with that star is that it contains very little carbon compared to most stars of those metallicities. This is a spectrum that we obtained from the VLT UVES, and you can see it's always fascinating to me to see these stars that contain hydrogen. You see a calcium line here, and then you see very little else in the spectrum. If this star were more normal for a star of that type, this is the amount of carbon that we would expect that would create these large bands that appear here in red. This is definitely not a carbon-enhanced star, and as such, it's quite unique in this regard. It might be the second most middle poor star discovered so far, and we are actively following it up to understand it better, along with another handful of stars of very low metallicity. I want to switch topic a little bit. We're covering a lot of topics within Pristine, but in particular, I wanted to talk about stellar streams. These are other fossils from the formation of the Milky Way. As the Milky Way is accreting globular clusters, dwarf galaxies, these end up depositing their stars in the halo of the Milky Way in the form of streams. And you can see here, so what I meant to say here is that another type of science that we can do with Pristine is look at stellar streams. These are the leftovers of globular clusters, dwarf galaxies that were brought in the halo of the Milky Way through hierarchical accretion and deposited their stars in the halo of the Milky Way. This plot that I'm showing you on the right is not from Pristine, but it's beautiful work that's been done by my collaborator, Rodrigo Ibata in Strasbourg, showing all the streams, about 100 now, that we're able to find with the Gaia data, Gaia proper motions, photometry, parallaxes, and so on. It's a beautiful wealth of these stellar streams crisscrossing the halo. And one thing that became very, very obvious is that we have this fairly wide Pristine survey. What can Pristine tell us about these streams? What is the metallicity of these streams in the halo? And do they look similar to the metallicity of, for instance, globular clusters that we know nowadays in the halo of the Milky Way? So this is what we did a couple of years ago. We have about 14 streams in common, a bit more than 14 streams in common between Streamfinder and Pristine. And you see the metallicity of the Streamfinder streams, the new streams that appeared in blue here, compared to known dwarf galaxies in red and known Milky Way globular cluster in black. And there's good reasons to think that most of these streams here are produced by the globular clusters that have been disrupted through tides. But it's quite striking that the metallicity of these objects is quite shifted to the lower metallicity compared to known globular clusters in the Milky Way. So it looks like maybe the oldest clusters of the Milky Way have been disrupted, or at least clusters that had properties that are not observable nowadays, with clusters of incredibly low metallicity. In particular, this guy here called C19 that we quickly followed up soon after its discovery, and using various telescopes, including Graces and Espadon here, we're able to show that if we take the 8 brightest stars in this system, they all have the same metallicity, and this metallicity is incredibly low. This is the lowest metallicity cell structure known. It has a mean metallicity of -3.4 and effectively no spread in metallicity. So it looks very much like a globular cluster, which we've now confirmed through follow-up high-resolution abundances to get the chemistry of these stars. And the signals we see there that is going to be submitted soon in a paper by Kim Ven do show without ambiguity that this is a globular cluster, but it's an order of magnitude lower metallicity than what we know around the Milky Way, than the lowest metallicity cluster we know around the Milky Way. So this is very much an exploration into the formation of the very first structures of the Milky Way, and once again, very complementary to what's been done at high redshift with these these clusters that are just forming right now that are observed through JWST images. Before I move to the future of Pristine, I wanted to point out that we have published the first data release, DR1, about a year ago. This is a mix of Gaia-based, it's effectively using the Gaia very, very low resolution spectra that the Gaia has distributed for fairly bright stars, brighter than G of 17 or so. We're able to integrate these very low resolution spectra onto the calcium K filter curve and effectively reproduce a pristine-like survey over the whole sky for the bright sky. So that's what you see here on the left with the footprint of that Gaia-based pristine all-sky survey. And for all the stars that are in this survey, we're also providing the much better quality, real pristine DR1 data. This is all public. There's about 35 million metallicities in this catalog, including a few thousand stars with good candidates with metallicity below -3 that absolutely deserve to be followed up. We will have, we've been discussing at a meeting a month ago about Pristine DR2 that will come out in early 2026, including all the data until more or less now. And so that'll go all the way down to the lowest magnitudes, the faintest stars, down to G of about 20 that we have in the 7,000-8,000 square degrees we've collected so far. So what is the future? The future for us is very much the WEAVE multi-object spectroscopic survey that should have started in 2021. Unfortunately, there's been a whole bunch of reasons why it didn't, including COVID, including Brexit, including a volcano exploding onto the island, and just the general complexity of putting such a large project together. But the reason why this is the future for us is that we are providing the candidate extremely middle-pole stars for WEAVE, which means that we will be building a sample, we think, of close to 10,000 EMP stars in the next 5 years. And that's going from only 700 known right now. So it's more than an order of magnitude increase. This is images of the facility that's on the WHT in La Palma right now, and getting ready to start observing by the end of the year. It's for this reason that we submitted, we answered the call for LPs and asked for 30 nights to cover the full extent of the WEAVE footprint. The benefit for us, the fact that it's been delayed, means that we have been able to cover a lot of the footprint already, which is what appears in black. You don't even see it in some regions because we've completely covered it. In other regions, there's still holes missing. So we've been awarded time to effectively completely tile up the WEAVE footprint before WEAVE observes, because WEAVE doesn't do any repeats. And so every field that's observed by WEAVE for which we don't have Pristine, then we don't have a good way to select these EMP stars. And so we'll start the LP in a couple of months. And we're very excited to start really tiling this region and filling out these holes. And just to finish, I just wanted to put back here the current timeline for the data releases with DR1 that has been published last year. It's completely accessible. Either you find it on ADS or Archive, or shoot me an email. I'd be happy to point you to it. It's about 7,000 square degrees of the bright sky. Pristine DR2 will come out in probably 6 to 9 months, and will be the whole sky that you see in red here on the right, down to the full depth of Pristine. And the final Pristine DR3, we've committed with the LP to publish the final data release about a year after the LP is finished. That will be about 2028, with everything we've accumulated in the meantime. And I'll stop here. Thank you very much.
Thank you very much. Really beautiful work, like the other large programs. Okay, questions?
Very nice work, Nicolas. This is Ting. So I saw that the DR1 for Pristine only goes to 17.6. What's the current plan for Pristine DR2? What's the magnitude limit you guys are planning to release?
It will be everything we have. So down to the full depth of Pristine. We're more or less tailored to the Gaia depth, although we're a tiny bit fainter. We go a tiny bit fainter than Gaia, but basically we'll release everything that we currently have as of now.
Thank you very much.